This is, as I said, an interactive tutorial. So if you haven't had the chance to download the slides and most importantly pull the Docker images, they are fairly large, then I'm going to be talking for some 10 minutes now to give you one last chance to do so. There is actually a prize at the end, so keep an eye out for that. So I just had a lovely introduction, so I won't spend too much time here, yeah, I'm based in Copenhagen. I'm Norwegian. My wife is Italian, so we have a multilingual household. I'm always thrilled to be here at PyData London. So, Apache Iceberg. First, before we can talk about Apache Iceberg, we need to talk a bit about where it came from. But I'm a bit curious, how many people are here because they've only heard about Iceberg and want to know more about it? Okay, who's been playing around with it, messing around? Okay, a couple. Anyone running in production? One? Okay, cool. And how many of you have worked with or are working with something like Hadoop? Okay, great. So in the beginning, there was Hadoop, and that was kind of the start of this ability to store and process large amounts of data. You know, it was okay. For those of you who are working with it today, you know that it works, but it's not the ideal situation by any means. And of course, when we have storage, then the next step is we want databases, right? So how could we add SQL onto this technology of Hadoop? And then we came out with something called Hive. Does anyone have worked with Hive yeah, we got the one. Okay, couple. So in order to understand a bit about Iceberg, you have to know that we're coming from this era of Hive, which has a number of limitations, and that's what they were trying to solve. I'm not going to talk too much about that today because I know that there are a lot of people in here who aren't in that situation, myself included. To me, the reason that Iceberg is interested is this idea of the decomposed database. So this notion, and I stole this completely from Voltron data, that what we want to do is we want to be able to separate our layers in our database, because when we tie everything up into one big database, then that makes us very inflexible and makes us very hard to move around. So this is the power of standards, right? So we all complain about another standard. The reason that we use these standards and have these standards is because it allows us to have this decomposing, this interoperability, where different technologies can implement these different standards. So I mentioned the Voltron data, the composable codex. If you haven't read this, I would definitely recommend taking half an hour out of your day and just going through this. It's an excellent piece of literature, which basically speaks to this idea of decomposing your data stack. They go even into more detail than I'm going to talk about here today. But I just wanted to plug it because that's where I took a lot of the ideas from. So just to touch briefly again on this idea of today, if you're running a classical data warehouse, you would look something like this, right? You have your servers, that your SQL server, your Oracle, your Postgres, and it runs on a physical server, and in that server, that is the total sum of your compute and your storage. If you wanted to, you know, spin up another database and I wanted to read from your Postgres database, I can't let you borrow my compute to read your data. I have to ask your compute to get the data and give it to me. So that means that we come up with all sorts of clever ways to scale. You know, we do sharding, we get a bigger machine. But in the end, what you really want to do is that you want to let everyone have their own compute and that the storage stays the same. So this is kind of the scenario that we want to go towards. And this is actually what a lot of the bigger data warehouses today, that your Snowflakes, your Databricks, this is the idea that they're built on and that they made their billions of dollars on. That the compute can be separate from the storage, and that you don't have to spin up your own service and storage and copy the data in. You get the zero-copy clones and all the good stuff that the vendors all talk about. But the problem with something like Snowflake and Databricks is that it's still locked away inside of Snowflake and Databricks. So is it really any different from this picture? It's just that now it's just called Snowflake and Databricks instead of Postgres and Oracle. So this is where standards come in and where Iceberg comes in. So Iceberg gives us a standard that anyone can then implement and then read that storage from. And now we're at the stage of a truly decomposable database where I can have my compute read your storage, even if you are in Databricks, even if you are in Snowflake, because they all speak the same language of storage. So that is sort of the motivation about the why. That's why I think Iceberg is very interesting, is because it gives me the ability to store the data once, and then all my different teams, they can read that data using the query engine that they're most comfortable with. So hopefully that was enough time for you to pull the notebooks and start getting some of these Docker images running. And then we'll jump into the first one. So it's always good to have a motivated example. Today we're going to be talking about housing prices. My brother lives in London. He bought a house a while ago. He's looking to sell it, so it was a bit of an interesting case to work on. And it turns out that gov.uk publishes a prices paid dataset, which is every single house sale in England and Wales, a property sale, I should say. So I thought that would be fun to play with. And of course, we have the license. Part of the license terms is that we show that the license is there. And make sure that you run these commands if you want to follow along. So let's jump into it. So Iceberg architecture in a snapshot. If you go home and you understand this picture, then you can call yourself an Iceberg expert. Because in the end, Iceberg is just a specification. It's just a way of storing data that allows query engines to do cool stuff. So we have a couple of different components here. And we're going to start at the very top with the Iceberg catalog. So the Iceberg catalog is basically what keeps track of where are our tables and what is the most current version of our tables. That's what the Iceberg spec says. Catalogs are also growing and can have a lot of different other cool functionality, but that's bonus to what the Iceberg specification is. So the first thing you need to do when you're on your Iceberg journey is to pick your catalog. And there are quite a lot of options. So sometimes those choices are made for you. If you're in AWS, you might use the AWS Glue as your catalog. If you're already in Snowflake, you probably want to use the Snowflake Open Catalog in Databricks, Unity, so forth and so on. If you're still on Hive, you can use the Hive Metastore. That's perfectly compatible. For this demonstration, I'm using Lakekeeper. The reason for that is it's a single binary that I can just drop into a Docker image and just run. It supports authorization, authentication, though we're not going to be going through that today. But the nice thing is that they all have this REST interface. And we have a library called PyIceberg, which we'll be using to interact with it. So the first thing we need to do is set up a connection to our catalog. So fairly simple. We have the URI to our Lakekeeper, and then we specify a warehouse, something that was created when you ran that bootstrap command. So in Iceberg, we don't talk about schemas and tables, because schemas is a bit of an overloaded word. So we're kind of moving towards namespaces and tables, and that's what Iceberg talks about. So we'll create a housing namespace, because we're going to do some housing data today. And then, of course, we have an actual schema, a data schema. So there are a few different ways to define a table. If you have a query engine that uses SQL, you can, of course, use a create table statements. We're Python here, so we're using the PyIceberg library directly. And it has all the different data types that are defined in the Iceberg spec, which covers pretty much most use cases. In V3, you're also getting geo types, so that's going to be pretty interesting too. But it kind of looks like this. You define a schema, and then you have nested fields. So you need a field ID, the name, data type, required or not, as well as an optional docstring. You can also add additional properties in here, but these are the ones that I tend to go with. Notice nested fields, so that means you can also have nested fields. So you can also have these recursive schemas if you want. We also have down here an identifier field. So that's, Iceberg doesn't have a primary key in the same sense that a relational database would, but you can still specify an identifier. And that helps when you're doing upserts, which we'll talk about in a bit. So now we have our schema. Then we need to actually create our table. So we give it a name. So you notice we have the housing namespace, as well as the table name, in this case, staging prices, our schema, and we can optionally specify a location, usually in some kind of object storage. So in this case, we're running Minio locally. You could be using S3. You could be using any kind of blob storage that you have. If you don't specify location, it varies by catalog, but the Lakekeeper catalog will generate one for you using a random ID. So that was kind of, now we have a table, but it's not actually that interesting until we actually put some data into it. So we have our bunch of CSVs, which basically look like this. And this is our housing prices data set. Because this is government data, they don't have nice things like columns. So we just put it into function so that we don't have to think about it again. But yeah, this kind of looks like. We have transaction IDs, we have a price, we have when did this transfer happen, and then a whole bunch of address data, as you would expect from a data set like this. So now we actually want to write some data. So in PyIceberg, we have 3 different methods of writing. We have append, overwrite, and upsert. Append, as you would expect, appends the data to the end of the table. Overwrite will delete the table and then insert the data, essentially append it. And then recently, I think it was only a couple of months ago, we got upsert as well, which we'll look at the join column or the primary column, and then updates existing data or append it if it is new data. So quick notes that PyIceberg is a bit stricter on schemas than Polars is. So Polars doesn't let you have field is required in its schema. So currently what we have to do is that we have to, because Iceberg is using arrow, we take the arrow table from Polars and then cast it into our PyIceberg schema. That way we know we're getting the same schema when we're writing. And then Iceberg is not going to complain. So this will take a couple of seconds, and then we should have a bunch of data in Iceberg. So one cool thing, notice I haven't actually put any S3 credentials into my code. The catalog is vending the credentials for me. So given that I'm authenticated to the catalog and authorized to write to the table, then the catalog is going to give me temporary S3 credentials to do the writes and the reads. So it's managing that for me. So now we're all done, and now we can actually look at some of the interesting Iceberg parts. So if you'll remember, we specified location as warehouse housing staging. Oh, the warehouse is because that's where we put the, what did I call it, the warehouse. And you'll notice we have 2 folders in here. We have data and we have metadata. So that is the magic of Iceberg, it's basically keeping track of everything using metadata. So that's why we have this separation. And we can ask our table object, where is this metadata located? So we'll see it's in this metadata folder with this, this is a sequential number, and then some random digits, gzipped metadata.json. So this is the first level of our Iceberg onion. So we have we call this a snapshot or metadata.json, which contains some number of snapshots. So we're at this level that we're operating right now. So because this is gzipped, we have to also, what did I not do? Oh, that's annoying. I didn't run this one. That was a bit important. So this is actually what the metadata inside of there looks like. Stop. So you can see we have a format version, always very, very important when you're writing standards. Include the version number in your metadata. We have a unique ID, the location of the data. We have some timestamps. And we have our schema defined right here. So you can see we have 16 fields. And if we open up one of them, this should look pretty familiar. It's also nice we actually get the documentation in there as well. So various tooling can actually extract and use that. But the meat is here in this snapshot. So each snapshot has a unique ID. It has a timestamp, and it points to a manifest list. You'll notice this is an Avro file. And we also get a summary of what happened in this manifest list. So each collection of operations, each transactions, is isolated into one of these snapshots. So in this case, we're appending data, and we have some metadata about how many records did we add, how many bytes was that. So now we're moving on to the manifest list. So the metadata.json contains snapshots, which contains manifest list. So one snapshot will point to one manifest list. And if we open up one of those, so luckily Polars also reads Avro, so I'm just converting it to a dictionary so our simple human minds can read it. You notice that we have a list of items, and that's pointing to a manifest path. So that's going to be the next layer of our onion, as you can guess. But notice we're adding all this metadata to each layer of the onion, and that's how Iceberg does what it does. It has access to all this metadata about our files. So it doesn't have to go down to the physical data and read that out of the raw data. It can get it from the metadata directly. So we are told which snapshot was added to, how many rows is in this manifest. It's a bit boring, of course, because we only have the one file that we've written so far. So that continuing on, we're at this level right now. So let's open up one of those to have a look at that. So again, that's a Avro file. So Polars helps us out. And now we can actually see, now we're at the level of actual data written to disk. So status 1 means that it's been it's added. And here we have metadata about this file itself. What format it's in, how many records does it have. We also have things like the column sizes, how many bytes they are, the value counts, the null value counts. So if you have nulls, we don't actually have to read the file to figure that out. And most importantly, lower and upper bounds. So you notice this is base64 encoded data, but the Iceberg reader can use these value bounds to basically do the pruning of the files before it even starts to look at them. So for each of the columns, it's recorded that metadata. And different writers can implement additional statistics. It's a bit up to the writer exactly what's in there. So, and finally, we're actually at the data itself. So all these operations get done by the writer before it even touches a single file. And that's kind of the big difference. So for those of you who are using Hive, Hive works more on a folder structure where you're looking through folders for files. Iceberg doesn't have that principle at all. It keeps track of each individual file and knows where each file is. So that gives it the ability to do a bunch of different metadata things that's a bit more tricky to do in Hive. So if we open up one of those files, you can see we've recovered our original data. And that's because there's no need to split this up. It's 704 rows. If we check out the data size, it's like 15 megs. That's tiny data in the world of Iceberg. So that's why we only get to one full complete file because Iceberg doesn't see any need to split it out. But again, that's all transparent to you as the writer. Iceberg will take care of that depending on the configurations that it has. So let's add a new file just to see what changes. So now we're going to play some Where's Waldo. What's the big thing that's changed? Any guesses? The format version stays the same because we're still writing Iceberg version 2. Snapshots, exactly. So remember, it goes through that same order every time. The metadata JSON gets updated with a new snapshot. It gets, we have the sequence number 1, that's one we looked at before. And now we have sequence number 2, which is pointing to a new manifest list. And no prizes for guessing what's changed here. We have 2 different manifests now in our manifest list. So now it's actually at the point where Iceberg can start making choices. Which manifest path should I open based on the statistics that I have? And then we can also see that the manifests themselves, so these are all the manifests, and now we have a second data file. So again, the whole point of a lot of these data lake technologies is just avoid touching files. So Parquet is immutable with an asterisk. So it's much more expensive to change something in a Parquet file than just to write out a new one and update the metadata to tell you that there's some data over here you also have to read if you're reading this table. So in this case, we're just appending. So the easiest thing to do, just write out a new file, add it to the metadata that there's a new file. So now if we look inside of our data folder, we'll see we have our 2 Parquet files written out here. So this is the rapid fire, what is the Iceberg metadata layer doing? So if you understand this part, you understand what Iceberg is. And everything that you can do with Iceberg is based on this metadata. So next we're going to jump into the second part. So this is the fun part, in the sense that as an analyst, as a machine learning person, you probably don't really care about the formats. You just care that you can read and write this data. And as I mentioned at the top of this, the really cool thing is that you can just shove this into any query engine that supports Iceberg. And in Python, there are quite a few already. So we can, of course, use PyIceberg itself. So now we're talking at the raw primitive level, so to speak. It's giving us a scan object where you can select fields, and you can select the row filters. So you can, for example, put a where clause basically on your data. Then you get the results out, and you can natively convert it to a DuckDB table, to a arrow table, to pandas, and then you can keep working on it like I'm doing here. Because expressing a group by in these primitives, you can do it, but yeah, I'm lazy and it wouldn't add much value. I can just shove it into polars and have that do the last mile for me. So notice this took around 6 seconds. If I run it again, most of the work is being done in loading the various metadata, converting, deserializing. So that's being cached now. So any future iterations on this table is going to be a lot faster. I'll also say that's probably the slowest one we'll see. So I can also use polars directly. So polars has a scan iceberg. I can just pass it this PyIceberg table object. It knows what to do with it. And that's actually a lazy data frame, so you can also push down the various predicates and all that fun stuff. DuckDB, great option. We have to do a bit more because DuckDB doesn't have fantastic support for Iceberg yet. They have created in lines with AWS to improve it. But now they also recently launched their own table formats. So let's see how that's going to end up. But basically, I can tell the Iceberg scan function where is my metadata, and it goes and reads that and does all those operations. It doesn't talk to the catalog directly. But it is fairly fast. So this is without any caching, right? Because now we're in a separate engine. It doesn't have access to any of that cache information. So now we've been through Python. We have DuckDB, which is written in C++. Now we're going to use Trino, which is a pretty common big data SQL engine written in Java. So once again, now we're in Java land. So that goes pretty quick. Remember, this is also not cached. It's, again, a separate engine. So unfortunately, Iceberg is still fairly Java heavy. That was a reference implementation. It's written in Java. So Java gets all the cool toys first. But that doesn't mean that we can't enjoy it in Python world. So one cool new library that I've been playing a bit with is Daft. So Daft is kind of like polars, except it's written to be distributed. So they implement their own like Iceberg scanning thing, where it can spin up a whole bunch of workers, and then each of those goes and gets the various pieces of the files that it needs. So it can go from local to distributed. And it's, again, written in Rust, which is the cool kid on the block, right? But yeah, so usually the workflow for most of you working in enterprises would be that you have something like Snowflake, you have something like Databricks. That's going to be your main workhorse. But you really want to spin up like a Databricks cluster or use Snowflake Compute to do a simple group by of like 1 million records? Probably not. So having this optionality, being able to choose the query engine that makes sense for your use case is really, really handy. Actually forgot to mention that dbt is also now supporting sort of Iceberg natively, that you can specify Iceberg in the configuration, and then it'll write everything and read everything from Iceberg. So, quick exercise just to get you warmed up. Now you have a couple of query engines to choose between. I'd like you to write a query calculating the average house price for your county. And if you're not from the UK like me, pick the funniest sounding one. So I'll give you a couple of minutes for that. Is anyone getting sticker shock? This is real data from I'll give you 1 more minute before we move on. All right, so I'm going to stop you there in the interest of time. How many managed to do it? How many almost managed to do it? So the idea of this exercise was more to notice that how much did you actually have to think about Iceberg when you were doing this? And how much were you just doing what you normally do when you write a SQL query or a polars query or a pandas query? So now we're going to get into some of the cool stuff that you can actually do once the data is in Iceberg. So this is kind of more in the realm of the data engineering realm, and especially if you're coming from the Hive world, this might blow your mind. For everyone else, it might be okay. But once your data is in Iceberg, you can do some interesting things. So let's say that as in real life, you know, we figure out we actually kind of need an extra column in our database, right? So we actually really wanted a loader that column so that we can see what data has changed in our database and, you know, keep track of that. So that's what we have done here. And if I now try to insert that data, I'm going to get an error that the table contains more columns because Iceberg has schema on writes. It's going to verify that you're not going to write data that doesn't conform to the schema, just like you used to from a relational database. So in many data lakes, you would now have to rewrite all your files to contain this new column so that you could actually keep your schema updated. But because we have this metadata level, we can just actually change the metadata, and then PyIceberg will read the schema information when it's reading the data from the parquet. And Iceberg itself is keeping us safe, and that's not letting us do something that's going to break the data. So you can't just change a string to a date time, for example. It's conservative in what it allows. So all I actually have to do is just update the schema, add a column, loaded at with my timestamp type, and that's it. Instant operation is just metadata. And anyone want to guess what changed since last we looked at it? Louder? Schema, yes. All we've done is just update the schema. We now have a second schema in here with schema ID of 1. Now we have 17 fields. And if we go down to the last one, we now have our loaded at column here. Interestingly, the Iceberg spec keeps track of what the current schema ID is, but it also stamps what each snapshot was written with, so that Iceberg knows how to handle that old data, that it's adding a null column if it didn't exist back then. So now if we append the data, we should get the expected result. We're not getting an error, right? It's actually writing the data. If we look at our new snapshots, I always forget if it's the prepend there. Yep, here we go. We have schema ID. Oops. There we go. Put it in the middle, of course. So this one is written with schema ID 1, and this one is written with schema ID 0. But what about the data that we already had? So as with any good relational database, you get nulls in that new column. So if you were to alter table and create a new column, you would have the same behavior. So this is a good example of where different query engines have different properties. So I could update my data using PyIceberg. It would just be a bit of a pain in the butt. And in SQL, I have this statement, update table, that will just do it for me, and I don't have to think about all the low-level primitives. So if I jump into Trino and say update housing prices to set loaded at to the timestamp where it's null, then I get the expected results. So again, I'm using the query engine that's fit for purpose. So for a data engineer, it might be easier to use the Trino interface so that I can write SQL. But as you can see, now I have updated all my values, 1.5 million rows, and now there's no nulls anymore. So one thing you have to be careful with, Iceberg, I mentioned caches the data from the catalog. If you do something in a different query engine, like Trino, you need to make sure you refresh the table object, else it's going to have stale metadata. But now we see we have another snapshot. And if we open this one up, we actually see a new operation. So until now, we've only been appending. But now we're doing an update. So that means we actually have to rewrite some data. But the cardinal sin is to actually touch files. So what Iceberg does is that it has this concept of delete files. So, and here's asterisk. Technically, row groups are immutable. You can rewrite a whole row group, but it's much easier to just write a whole new file. So in the v2 specification of Iceberg, there are two different types of delete files. There are equality deletes. So basically, it would have the column name equals some ID, and that would mark that column, that row as deleted. You can also have positional deletes, which will look kind of like this. Again, a file name and the position in the file, which is deleted. So row 0, 1, 2, 3 are marked as deleted. So again, we're not actually touching existing files, we're just writing new files. Much cheaper in a data lake world. And in v3, this is going to be improved even more. Delta Lake, Iceberg, they're actually talking together and working together. So Iceberg is stealing deletion vectors from Delta Lake, and it's coming in v3, which is coming pretty soon. So we can use the Iceberg library to inspect various metadata, including what are the delete files. So we can open one of those up, and you can see exactly that. With this data file is marked position 0 as deleted. So Iceberg will read this file in, and then it'll just filter out those rows when it's reading the data. The final neat trick, everything is metadata. So that also includes the names of columns. In Iceberg, everything is referred to by that field ID that we set in the schema. So the names are just arbitrary metadata on that field ID. So if you want to rename it, that is basically a zero-cost operation. So loaded at, maybe we have a new naming standard. Everything should be _DWH. And data transfer would actually be really nice to have at the front end of the table. That's it. We're just changing the metadata. And now we have data transfer first and DWH loaded at as the name. So we now have a new schema ID 2. And you can see that in position 0, we have the ID 3 data transfer. So we just shifted around that array of columns. All right. So on to the next one. And this one, to me, is also one of the real killer features of Iceberg, time travel. And time travel is one of those things that once you understand what the metadata architecture looks like, it enables cool things like time travel. So we get a handle to our objects. So we have a full history of what's happened to our table. And you can do it from Python, you can do it from SQL. But here we can see every single snapshot that we've done so far, including the timestamps. You can also use SQL. They often use this $history, so $something, as to indicate I want to access the Iceberg metadata of this table. So this looks pretty much the same. So currently we have around 2.5 million rows. But this is where I need to copy paste, because again, these snapshot IDs are non-deterministic. So I can actually select what my table looked like as of a given snapshot, because all I'm doing is just reading a different snapshots inside of my metadata file. So this is basically free to do this time traveling. So in PyIceberg, you can of course do something similar. You just have to pass the snapshots ID. And most of these Python libraries, they build on top of PyIceberg, so they have a similar API. So there's something similar in Polar, so look like this. In SQL, however, there is some niceties. So for example, one cool thing you can do is specify the timestamp you want to see. So today is the 6th and 08. So if I wanted to see the data as of, let's say 20. Now it'll take that timestamp and find the closest ancestor and get it from there. So if you have your data pipeline breaking in the middle of the night, you can actually say, I want to see what the world looked like 1 second before that pipeline ran. And all of a sudden, I have access to exactly what happened. But again, us humans, we're pretty bad at remembering snapshot IDs and timestamps. So in Iceberg, you also have the concept of branches and tags. Branches is a bit more in the future that it's generally available, but you can actually do things like create a Git branch, in quotation marks, of your data, work on that, and then merge it back into your main branch for everyone to see. That's currently available in Spark, but not in the other implementations as of yet. But I'm really looking forward to that being general purpose. Oh, I need to change my... So what I can do is I can create a tag, initial commit. And now I have a name for that snapshot ID. And this could be, Q3 reports. This could be customer A reports. And now I have a reference, initial commit, that's listed. So this is actually part of the specification itself. You'll notice how we're actually on the main branch as well, right? That's keeping track of what the current snapshot ID is on that branch. So now I can do the same, but I just have to reference initial commits instead of some arbitrary snapshot ID that I had to go to the history and copy out. You can also do it in PyIceberg. So again, it's a bit more cumbersome because you don't have that direct access to it, but you have to look up the snapshot ID of a name. But of course, it's completely possible. So one really nice thing as well is you can also do rollbacks. So instead of having to, like in Git, you mess something up, roll back. You can actually publish much more aggressively in the knowledge that if something goes wrong, you can always roll back to a state at a given time. So if we look at the current state of the world, it looks like this. So when I'm selecting without anything, it's selecting as if the current version is the first one. Make sure we refresh our metadata, just to show that is the same. All the other snapshots are still there. We haven't touched those. We've just moved the pointer inside the catalog. So the last part is around cleaning up. So as you can imagine, as you're appending more and more data, you're getting a new snapshot every time. If you try to do a transaction, so Iceberg does implement ACID transactions, and it gets aborted, you'll have written some data files that aren't referenced anywhere. We call those orphan data files. So PyIceberg is implementing table maintenance functions. It's one of the milestones that they're working on. So currently we're using Trino for that. I've also configured it to allow, by default, the retention threshold is 7 days, and you can't go below that. That's configurable. I set it to 0 days for the purposes of the demo. But I can expire the snapshots. So all the snapshots that are older than X, get rid of those. We're happy with those. We don't need those anymore. Orphan files. So these are those abandoned files I mentioned. You can also optimize the manifests. So you can co-locate them so that they're easier to read. And then there's a general optimize. So this is solving what's called the small files problem. This is very common if you're doing, for example, streaming workloads. You'll have data dripping in, and you'll end up with 2 meg files, 3 meg files, 5 meg files for each batch that gets committed. Small files is the killer of anything that has to do with object storage because you need to send a lot of different API requests to S3, and then you need to have that file I/O of actually opening those files and reading them. So the rule of thumb is you want around 128 meg to a gig per K file as a rule of thumb. So that's what the optimize functionality does. It just takes files that are underneath that threshold and then rewrites them. So this is now we're explicitly allowing Iceberg to take the time to rewrite those files, actually physically rewrite them, and deleting the old ones. We don't have that much, so all cleaned up. And now we don't have any old snapshots anymore. Now we're clean in that sense. So moving on to partitioning. Yeah.
Before you were doing the cleanup and after the rollback, so the rollback is described as a permanent activity, right?
Yes.
When you do the rollback, you could still see the pre-rollback snapshots.
Yes.
Does that mean that the rollback can be rolled back as well before?
Yes. So the cool thing is that all you're doing is moving a pointer in the catalog. So that's the catalog doesn't know anything about the order of snapshots. It just says this is the current snapshot, and you can ask to see another one. So partitioning, if you have worked with data lakes before, partitioning is the indexing of the data lake house world. So you do want to speed up queries, but you don't have access to a classical index as you do in a database. So this is one of those things where you kind of have to understand how it used to be before you see how it works now. So I'm going to spend 2 minutes talking about Hive partitioning, which is still fairly common in a lot of areas because it's the best we had. So you can imagine you have your folder structure inside of S3, where the folder name is year equals some value. So year equals 24, month equals 01, day equals 01, and then we get to our files. So that way, if I have a query that wants all the files in 2024, I only have to read everything that's inside of this folder. I can skip the entire 2023 and older folders. So potentially that's a massive speed up in terms of reading the data. And so forth, same with the month and the day, right? So if I wanted the 1st of January, I only have to read these 2 files and nothing else. So the problem is that very often you want to write a query kind of like this, where I would say between 2024-01-01 and 2024-02-28. In the old style of partitioning, you can't do that because that's not in there. There is no folder called 2024-01-01. So you would need to decompose your logic. You need to know about the partitioning schema of your data in order to write effective queries. So that's why we call that more explicit partitioning. You need to have that knowledge to write explicit partitioning queries, or else you'll destroy performance and you don't even know why. So Iceberg has what's called hidden partitioning as opposed to explicit partitioning. So if we clear out our table just to start from a clean slate. So now I have my table object and I can implement what's called a transformation. So I can say that the date of transfer field is partitioned by month. So what Iceberg is doing is that it's registering that there is this transformation on this column, and when I execute a query that touches that column, the Iceberg engine will then convert my query to match that partitioning. And again, that's a metadata level operation, so it takes an instant. And now, looking back at our trusty spec, we have partitions, which we skipped over before, because before it was empty, not very interesting. Now, we've registered in the metadata that there is a transform month on source ID 3. So source ID 3 is the date of transfer column. Everything is done by IDs in Iceberg, as you remember. So just to make it more interesting, let's load in some more data. So we load in the first file, and now that we learned about tagging, that's good practice, right? To add a tag to our load. You can imagine we're doing monthly loads of this housing data, right? So let's let that run. One thing I didn't mention, so tags, you can set the expiration of a tag. So you can say that this tag should be valid for a certain amount of time. So currently I'm setting it at a month. And then it won't be touched by any expire snapshots or any cleanup operations until that threshold is exceeded. So now we've finished, and if we look inside of our 3 buckets, we now see we're actually still using that same style of partitioning, right? So we now have a folder that says month date of transfer equals some value. And just to show that how we're taking advantage of this, I use my favorite Worcestershire. And then we can look into the query plan, and at the very bottom down here, Worcestershire we didn't do anything to, right? That's a plain old query where we're filtering. We're actually throwing out 98% of the data, right? So we're reading everything, and then we're throwing out 98%. If we do the same thing on a data interval, you can scroll to the bottom, Now you can see we've added a constraint on data transfer because the query engine has noticed, hey, there's a transformation going on here. And now I'm only getting this interval, and I'm reading 2.12 megabytes instead of, what was it, 8.9. So now I can use that partitioning to go straight to the file. But you notice that my query, I didn't have to know anything about exactly how it's partitioned. Is it year, month, day, something in between? I'm just writing a SQL query as I normally would, and now kind of more like in a relational database, you need to know what columns have an index on them to take advantage of it, but that's all you need to know. But how big are these files that we're scanning right now? So remember that I have the small file problem. So this file is actually only around 2.7 megs, which is pretty small. So what's the threshold at which you're actually wasting more time by reading lots of small files compared to this time saved by partitioning? So as I mentioned, the ideal is around those 128 to 1 gig. Of course, test and verify on your own data, but we probably want to upgrade to a higher granularity on our partitioning. So in the old world, we would not have to throw out all the data, rewrite all the data, because we wanted to go from a month partitioning scheme to a year partitioning scheme. Iceberg, it's a metadata change. So you can only have one per column, so we need to remove the old one and then add in a year transform onto our data transfer column. So now if I read in the next file, because we're just doing a metadata operation, we're not touching any of the old files. The old files will still look the same, but if we look at the new file structure, now you can see that we retained all the old ones, but the next file we're writing in is partitioned on year. So this is around 23 megs. So the 128 number is uncompressed data. Parquet is pretty well compressed, so we're getting closer. Obviously, we're not dealing with lots of data just because it would take a long time to load for this demo. But that's definitely better. So let's just load in the rest of these files. And now you can see that we have 2015 partitioned by month, and the rest is partitioned by year. So Iceberg can actually keep track of what data is loaded with what partitioning. So it actually creates two different partition plans for a certain interval, and then a new partition plan for the other interval. So when it's actually fetching the data, it's using two different mechanisms for reading that data. So if we look at our query plan again, same thing. We haven't touched it. We're throwing out 98% of the data. If we try on here, you'll notice we're still having a constraint on data transfer. And it can do it even though we're in 2015, which was month partitioned, and the rest of it is year partitioned. It still figures out how to write that query so that it's optimal. Obviously, we're reading more data because we have more records, but we're not reading in all the data and then throwing it out. So that was the features part. So now we're going to go into a bit of the data engineering. Yeah.
Would you be able to do partitioning based on sort of composites?
Yes, actually, thank you for reminding me. So the question is, can you do partitioning on something else? And the answer is yes. The Iceberg specification has, I'd say, 8 different transformations it supports. That's bucketing, it's hashing, it's truncating. So like if you have a string, you can take the first X characters, year, month, day transforms built in.
And combination of keys, like year and count, for example?
You can have as many transformations as you want on different columns, but not on the same column. So if you were to do multiple transformations, it would nest those folders underneath each other. So you just have to think about the order of that as well, right? So, but we had the motivating question in the beginning around house prices. So what I was actually thinking about was let's massage this data into something that can actually.
This is a building announcement. The fire alarm system is about to be tested. No action is required.
Yeah, so 10 o'clock.
This is a building announcement. The fire alarm system is about to be tested. No action is required.
So
This is a building announcement. The fire alarm system.
yeah, they said it was 10 o'clock. So let's quickly run through this so that we can have some data loading. But the details aren't that important. This is more like what a data engineer would do with any kind of data. Creating a dimension, we're creating a hash key on those address fields because we don't have a nice address ID. We're creating a fact. So when we load the data, there was is this data new? Is it changed? Or is it deleted from the previous month? So we write some SQL to take care of that. So again, our data engineers are happy because they get to do the same thing that they always do. If it was a SQL server, if it was Postgres, this is the kind of SQL that they write every single day. So we can run those two. So just get that running before we have 1 minute left until the fire alarm test starts. So what that's going to do is it's going to give us a nice clean fact and dimension that we can then use to answer some interesting questions with. So this is running inside of Trino. So again, there's no caching of any of this. It's starting from scratch. And that would be a good time for the alarm to start. So, all right, so there we go. And now we have grab a handle to our new table. And
Attention, please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts. Attention, please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts.
all right, we hope that was it. So thank you for your patience. Let's get back to our regular scheduled programming. So what we did before, we loaded that data into a new table. And now we have it for a change of pace. We can actually switch over to using polars. So what we're trying to do here is figure out what my house, what the average price of a house if you bought it.
This is a building announcement. Testing of the fire alarm is now complete. Please respond to any further alarms. This is a building announcement. Testing of the fire alarm is now complete. Please respond to any further alarms.
All right, I think we're good to go. So what we're trying to figure out here is what are the profits of the various houses that are bought and sold in the UK. So what we're doing here is a bit simplistic, but we're taking what's the first sale of a house, finding what's the last sale of the house, and then doing a subtraction of the cost of those two to figure out what's the average profits that we're getting if we were to buy a house and sell it later. So I could write this in SQL, I could write this in Daft or Polars or DuckDB, but we're using Polars here. It has a nice windowing functionality. So now this is running in Polars, which is pushing the predicates down to the Iceberg layer. So it's running fairly quickly, even though we're talking 7 million rows, and doing a lot of windowing, a lot of fairly complex operations. And we have around, because we're filtering out all the houses that haven't been sold. So if you just bought and hold, then we don't know about you yet. So this is actually every single house in the UK that was sold between, I don't forget what the original start date was, 2017 to today. What was the profits on that house? And now we're pretending that you bought it and then you sold it at the very end. We're not looking at the intermediate purchases. So we can throw that into a table. So because Polar is arrow behind the hood, we can also use the schema directly from Polars. We don't get the doc string and the required, but for something like this, where you just want to throw it into a table for further reuse, it's a one-liner to get that. So then we can overwrite, because this would be a process where you overwrite the current data. It's just giving us a warning because it's doing a delete but didn't find any rows. So it's just letting you know that, hey, you asked me to delete something that wasn't there. And just to round out the query engine jamboree, we can use Daft to read in that data, and then let's grab the mean profits per year. So if you was this the first day? If you bought a house in 2015, your average profit was 66,980 pounds. Yeah, it was better back in the day. Obviously, we're having a bit of a time bias because recent houses haven't been sold yet. So it's a shorter duration that they've had to sell. But for the purpose of the exercise, it works nicely. So this is more like the classical data engineering thing you'd have to do. And again, your data engineers will be very happy because they don't have to change the way they work. So now we're ready to answer our motivating question. Is your house worth its weight in gold? So I thought it would be fun to compare houses to other asset classes. I am an asset manager after all. So if you were to buy gold instead of buying a house, do you think you're better off or worse off? Without skipping further down. Better off? Worse off? Better? So breaking it down, we're going to load some gold prices into Iceberg. We're going to load some exchange rates because all the gold prices are in US dollars. And then for each row in our profits table, we want to do the hypothetical. If I spent the money that I bought on a house to buy gold, how much gold would I have? And then at the end of the period, given that amount of gold, if I were to sell it, how much would I have in pounds? So again, we have all these niceties in terms of schemas. So we make it commodities namespace. We throw in a gold schema. We create a table around that. I just wanted to show you that you can also define upfront these various partitions, right? You don't need to manipulate the metadata. Upfront, when you create a table, you can add a partition specification. So in this key, we're doing it by year. Bit overkill because it's 1 row per day, so not a lot of data. But I just wanted to show you this is what it looks like. And we write it into our table. So one thing I wanted to point out is that Iceberg does have decimals, very important in this line of work. So even though the prices are loaded in float 64, Iceberg will convert that into a decimal and try to keep the precision. Similarly for FX rates, so we create a new namespace, and then we read in our FX rates. So what we're doing is we're creating currency pairs. So you can imagine in the future we might want to have different currency pairs. The price is not necessarily exchangeable. So the GBP to USD exchange rate might be different than the USD to USD GBP rates. And now comes the business logic. So this basically just, we don't need to go into the details of it, but just like I mentioned, what we're doing is figuring out how much gold we would have had, how much gold would that sell for, how much would that sell for at the end of the period for each one. We run that. So one of the things I want to point out here is this workflow doesn't really mean that you need to know anything about Iceberg. And that's kind of the point of Iceberg. So Ryan Blue, the creator of Iceberg, when he gets asked about these format wars, because we have Delta Lake and we have Iceberg and we have Hoodie, his point of view is you shouldn't notice. The Iceberg layer should just disappear into the background to let you do work. And I think Iceberg is really good at that. It's like you have a little bit of boilerplate in the beginning to set it up. But like in Trino, that's pre-configured. I've added a connector into Trino. So that's part of the deployment of Trino itself. I don't actually need to know anything about the Iceberg catalog or anything like that. That's done for me by my infrastructure team. So now we have our data all configured. So if we describe it, you can see we have the gold profits here, and we have the house profits. So far, gold's looking pretty good. We have the percentiles here. Yeah, gold looking pretty good. Then one of my favorite ways of looking at data like this is putting it into quantiles. So if we divide it into what's the gold, the housing, the gold profit minus the house profit for the different quantiles. So at this end, then your house is better off. And as we move up, we're starting to break even closer around. So 24% of the houses sold made more money than if they bought gold instead. And if we keep on going up our quantiles, then you can kind of say, how lucky would I have been? You can roll a D80 and see how much money you would have made by buying gold instead. So another quick exercise. So this is the whole UK. Obviously, London and Cardiff looks quite different. So now you have the data. Try writing a query that would calculate this for your own region. And if you don't have a region, then pick the silliest one. So we have 20 minutes. And I do have one bonus item that I would like to show you. So I'll give you 10 minutes for this item. All right, so I'm going to stop you there. Did anyone manage to get some results? So, but did you have problems on the Iceberg part or the logic parts? Infrastructure. Ah.
You can change the allocation Docker, but it doesn't fix it for the gold versus house prices setup. So like, I think in the previous notebook in data engineering, it struggles and crashes. And then I increased it to 32 gig. So it can do notebook 6, but then it can't do notebook 7.
Yeah, I've heard that's a good point. You probably should have told you to kill off some of the old kernels if you're running out of memory, because each of the notebooks keeps everything in memory, of course. So, but all right, let's move on to the last parts. So one of the really cool use cases of Iceberg that is popping up recently is in the domain of streaming. So for those of you who worked in that space, you may have heard of Lambda architecture and Kappa architecture. But it basically boils down to this idea that you have a lot of events, right? So you can imagine that we were getting, every time a house was sold, we would get an event that's with the price of that transaction. And that lets us do some interesting things in terms of setting up subscribers, in terms of keeping a live count of what's the average in your region, so that you can perform some action. Maybe you want to trade when the average price is at a certain level. Which is great for that moment, but if you work in analytics like myself, then working with a stream that's on a Kafka topic can be quite challenging, because you want to do a 10-year analysis. You want to train some machine learning model where you need the whole data from the beginning. So a lot of different ways in streaming have been looked at to give you that offline capability, in a sense, where you're reading messages and storing them so that for analysis later. And Iceberg turns out to be quite a good fit for this. So in fact, both Confluent and Red Panda is actually doing this natively under the hood. So they're storing the data in Iceberg when you're putting it into what they call tiered storage. And Confluent just released something called TableFlow, which is also sort of a one-click button thing to take a Kafka topic and put it into an Iceberg table. And that lets you have like the best of both worlds. You get to have the reactivity of working with events, but you can also have that offline analytics where you can do your 10-year analytics. So just to show that off, if you want to do this, then there was a bonus Docker Compose file that spins up the Kafka infrastructure. The first thing we need to do is to define our housing prices aggro schema, because that's what the schema registry expects, and that's what the setup our connector that's going to take the data from Kafka and put it into Iceberg is going to use that schema to create our tables. So in the Kafka ecosystem, you have a schema registry where you can register schemas, and then you can serialize and deserialize data that's coming into and out of Kafka, because Kafka is just the stream of bytes. So we set up QuickStream because I was told to get bonus points if I do that. To basically talk to my Kafka broker, I create a topic for my housing prices, and then let's push some data into our Kafka topic. So reading in one of the CSVs, and then serializing it to Avro and pushing it to my Kafka topic. There is also this handy dandy overview here where you can see we have data in our Kafka topic. So you can imagine this will be coming in continuously as houses are being sold. So again, in the Kafka ecosystem, there's something called Kafka Connect, which is basically a piece of Java that knows how to read from a Kafka topic and write to something, or vice versa. So there is an Iceberg sync connector. So we set it up to talk to our catalog. We say what table is going to create. It also has what's called a control topic. A control topic is a way for it to synchronize. Kafka Connect can have many different workers. They need to know which files have been written and which haven't. So they put that all onto a topic. We can also tell it to create the table for us and evolve the schema. So if I were to change the Avro schema, then I want the topic to actually create the new columns inside of my Iceberg table. And then we just say it's in Avro, and this is where you can find the schema. Just to point out, I've changed the commit interval. Default is 5 minutes. That's a bit long to wait for a demo, so I've reduced it to 10 seconds. Don't do this in production. So now I can post that config. Let's check the status. Everything is nice and running. And that's just kind of happening in the background. So I will use my data grip, which has a Trino integration here. You can see all the tables and schemas that we had before. Hopefully, we should have a streaming prices. And 10 seconds haven't passed yet. We can also, this is a part of the live demo where, come on. There we go. So now I have basically some infrastructure just sitting there. Every time a message comes in on Iceberg, it'll batch that up so that you can configure like how, because again, small file problem, you don't want to write a single row to the Iceberg table if you can avoid it. But also you don't want to wait too long to get that data, so you have to find that sweet spot. When it hits that batch, it'll write that batch into Iceberg, and now it's available for all my analysts to play with. So there you can actually set, like you can let your customers know that every 15 minutes you actually have a complete set of data, which can be pretty powerful. So this is just a little bonus because I thought the fire alarm would take a bit longer. But I think it's a pretty cool architecture to set up. And we have a final exercise. This one is more of a take-home exercise, and that's where the prize comes in. So now we calculated if your house is worth its weight in gold. But there are many other exciting asset classes out in the world. So I've included a couple in the data folder here. It's always fun. We have Apple stock, we have Greg's, we have Wetherspoons, we're in the UK after all, Nordea, Novo Nordisk, and S&P 500. So those are like pre-canned data sets that you can play with. But anything that has a time series on a date level that you can find on the internet, you can try to calculate what is more valuable. And to the most interesting use case, if you find something cool, find me by the end of the weekend and you will win some Danish cookies, which they actually don't sell in the supermarket in Denmark because we don't eat these, but they look pretty. So that's your challenge for this weekend, and thank you very much for your time.